So let's kind of talk about the process of this, is what we're trying to do. The goal of these inference procedures is when we want to compare two different treatments from two different populations. This is different than a matched pairs design. These are independent samples. So most likely we'll have two different sample sizes that we're actually going to physically compare and kind of ask ourselves, is there a difference between one treatment versus another? And when we compare, we'll kind of think about the means of each of the samples and see if there's a difference between the actual means. And again, we're checking that these are independent samples from each other. All right, as far as assumptions go, somewhere in the problem it needs to state something about having an SRS or randomness. This can be stated explicitly, or this can be assumed. Just it's something we have to consider about looking at the data. We also need to make a statement about independence, that knowing one sample does not give us any more information about the other one. And we need to check normality. The typical normality conditions being either the samples are large enough, meaning we've got at least 30 in both sets. We could look at some sort of graph, histogram, box plot, normal probability plot, all the valid graphs that we've seen in previous distributions as far as checking for normality. And then the last condition is we're going to have to make some sort of statement about whether we are aware of the population standard deviation or not. If we know it, then that would be more of a Z procedure. And if it's an unknown, which is most likely what we're going to be looking at, then that would be a T procedure. Okay. Z procedures involve standard normal curves, mean of 0, standard deviation of 1, whereas T procedures involve degrees of freedom. Now, as far as finding degrees of freedom, we've kind of got two options. Option one, which is a slightly conservative approach, is we look at the two sample sizes and we use the smaller of the two. So whatever number is smaller, just subtract 1, and that's the degrees of freedom for it. The calculator can actually give us a slightly more accurate approximation for degrees of freedom. So sometimes it will actually have a different value when typing it in the calculator, and that's because that uses this lovely formula here, and I would not expect you to do that by hand. Okay, confidence intervals. This is the same process we've seen over and over again. The statistic is going to change because we're dealing with two independent samples. And the standard deviation process, that's going to change as well because we're dealing with means instead of proportions or other things. So our statistic is going to be the difference of the two means, x bar 1 minus x bar 2. Critical value in this case is T star, and that's based on the confidence level that they give us and the degrees of freedom. So that particular value will change depending upon what information they give us. And then our formula for standard deviation of the statistic involves, sort of looks like the Pythagorean theorem of sampling error, but we're going to take this sample standard deviation of the first one divided by its sample size, squared the standard deviation divided by sample size, and then add it to the square of the second, and then take the square root of that. The stuff inside the square root we refer to as standard error, and then when you take the T star into account, that's called margin of error. Okay, pooled procedures. Pooled procedures, this is used when we're dealing with two populations with the same variance. And the idea being that when we pool, we average the two sample variances to estimate a common population variance. Sort of the idea that we understand that the two samples came from a larger population, and so we would estimate or we'd pool these variances together. We actually are just going to ignore that idea. So bring it up, but it's not really going to have any impact on our calculations. And a lot of times the calculator again will do this for us. And we will, if there's an option for pooling, we'll just click no for that. Alright, so let's jump in and look at an example. Two competing headache remedies claimed to give fast-acting relief. An experiment was performed to compare the mean lengths of time required for bodily absorption of brand A and brand B. Assume the absorption time is normally distributed. 12 people were randomly selected and given an oral dosage of brand A, and another 12 were selected and given an oral dosage of brand B. The length of time in the minutes for the drugs to reach a specified level in the blood was recorded, and the mean was given below. Okay, we're going to start with looking at the shape and standard error for the sampling distribution of the mean speed of absorption. Okay, so for starters, when we look at the sampling distribution, let me kind of back up a second. In the problem, it actually told us that the samples were normally distributed, which means if the samples are normal, if the population is normal, then the samples themselves have to be normal. So we know we're dealing with a normal distribution. As far as standard error goes, I'm going to backtrack to that lovely formula we had a second ago. That's what we're doing right there, is that square root process to figure out what the standard deviation of those two samples are. So kind of get forward back to where I was. Alright, so if you'll take out your calculator, we'll actually write out the formula and then calculate the standard error. Okay, so this is the standard error part of our confidence interval formula. So we're going to identify those numbers and then just evaluate it on the formula and come up with an actual number. Okay, so I want the square root of these two fractions here. So let me get a plus going on in between. Okay, so I want the standard deviation of the first sample, which is 8.7, and then I want to square that, and I want to divide that by the sample size, which is 12. And then I want to do the same thing with the other one, so that'd be 7.5 squared divided by 12. Okay, so then we're going to take out our calculator. And let's get those decimals first. So 8.7 squared, and I want to divide that by 12. And then I want to add the other fraction next door to it, so 7.5 squared. And then divide that by 12. And so this will give me the decimal that's inside the square root. And then I want to take the square root of that number. So I can either just, if you have the ability to copy and paste, that's usually easier, or you can just copy the decimal down. And I get a standard error of about 3.32. Okay, so we just calculated this as far as our normal distribution goes. And then the second task is to create a 95% confidence interval difference in the mean lengths of time required for the absorption of each brand. So we're going to go through the mechanics first, and then I'll go back and show you how to set it up using your calculator, how to actually type in these numbers and get the same thing that I'm setting up on the screen here. So first, let's jump through our assumptions. I have two independent randomly assigned treatments. Just kind of backtrack for a second. If you think about where we got these numbers from, we picked two groups of 12 that had nothing to do with each other, and we gave them two different medicines. And we kept track to see how long the body would absorb the particular medicines. If I'd taken the same individual and, Monday gave them one medicine and then a week later gave them a different medicine and I tracked it, that would be a dependent sample, and I would go at this process entirely different. But because I used two different groups that had nothing in common, those are two independent samples, and they did mention in the description that it was randomly assigned treatments. So in that event, we've satisfied two of our assumptions in one. So independence and random. They did mention that the population, was normally distributed. So then the sample is also normally distributed. We don't have to check anything on that. And it's my favorite assumption that the standard deviation is unknown for the population because I don't know it. No, they didn't say it specifically. And again, it's that's the whole reason why we're doing a confidence interval, is to get an estimate on that. So it doesn't make sense that we would know it, because if I knew it, then why would I be estimating it? Anyways, okay, next step is the formulas and calculations. And you're probably thinking, how did they get the degrees of freedom of 21.53? Remember, there's two routes to get here. One is to use the lesser sample size, n minus 1 of it, or have the calculator work out the that lovely formula we saw earlier. So in this case, the calculator worked that out, and again, I'll show you how to do that in a moment. If I did it by hand rather than using the calculator, then let's see, both of them are sample size 12, so my degrees of freedom actually would have been 11. But this will be slightly more accurate, a little more, give us a little more better estimate as far as what this is doing. Okay, then from here we're just going to fill in our numbers. So we have the mean of the first one being 20.1, the mean of the brand B at 18.9. Let's see, then we have to calculate degrees of freedom for the sample size that they gave us, which is where they get the 2.08, and again I'll come back and show how we got this. And then that's the same formula for standard error with the 8.7 squared over 12 and the 7.5 squared over 12. And then they worked out and got those lovely numbers. Okay. All right. So let me kind of pause it here, and let's take out our calculator and let's get caught up to this point as far as how we got all these numbers. All right. So if you'll go to your calculator, turn it on. We're going to go to Stat, and we're going to arrow over to Tests, and we want to find a two-sample t interval. Two-sample t interval, which on my calculator is choice 0. Anyway, so look for two-sample t interval, and here we get kind of two choices. We could either input it with data. So if I had the raw data in the lists, and I could have it, list 1, list 2, I could type it in that way. Or in this case, we have the statistics. So I've got the mean and standard deviation and sample size, so I can do it that way. Okay, so I'm just going to input the mean of 20.1 and the standard deviation of 8.7, and then n being 12, and then the second sample mean is 18.9. The second standard deviation being 7.5, and then that sample size being 12. And then, let's see, we're actually doing a 95% confidence level, so we want to switch that to be 0.95 in case it's not. And if you remember, earlier I talked about we're just going to say no to pooling, and then we'll go ahead and calculate that. Okay, and so notice the calculator did that lovely complicated formula on degrees of freedom of 21.53, and that it also gave us the same confidence level that we had on the slide.